I apologize for not starting this at the beginning of class. Sorry. Sorry. What's at the bottom here? It says, when you put ammonia into water, what gets formed here? What's that right there? Ammonium ion, and what else? So that's why ammonia in water would be a base. But what does it say there? Strong? 100% of them do that? It says weak, doesn't it? So it is an electrolyte, but it's a weak electrolyte, isn't it? Yes?
I'm not sure what class I was in, but I remember it might have been chemistry sophomore year. We talked about like electrolysis, like splitting atoms with electricity. Does that have anything to do with the electrolyte quality?
The only thing it has to do with is if you use pure water and you hook a battery to it, you may not get any results because pure water is a non-electrolyte. So anytime you see electrolysis occurring, there's a little trick they don't tell you about. They usually put some kind of ionic compound in there. I use salt. I put a little bit of salt in there, and now I got a bunch of ion floating around. Now I'm going to hook it up to the battery. Then I get a lot of electricity going through there, and then I get a lot of electrolysis.
Okay.
So the only thing that would happen is the actual electrolysis itself is not that. That has to do with whether or not my battery will conduct electricity through the water.
Okay, got it.
So yes.
So, the molecular difference between acids and bases is that acids have hydrogen ions and bases have hydroxide.
And that's until next chapter. Until next chapter, that is true.
Do acids chemically react with things by the hydrogen ions?
Yes.
Or the
Yes.
And,
See, if I have HCl, the chloride ions might conduct electricity for me, but they have nothing to do with the acidic nature of me. I have all my acids are going to give hydrogen ions off. See that? That's going to make the acidic nature of an acid. Well, again, next chapter, guess what? Next chapter is the one you guys will have peer group teaching, and it's all about acids, bases, and pH. And I'm going to wait till that chapter gets here because there are 3 definitions for acid, not this chapter. This chapter just has one, and it's the Arrhenius definition. What is the Arrhenius? Remember this guy, Arrhenius? Have you read that yet? He's kind of big. Do you know at one time nobody thought, they didn't know what ions were. They didn't know what's an ion? What do you mean an ion? They thought, well, all lithium atoms are the same. They didn't know about ions, did they? And they didn't know about isotopes either. So here's this guy says, I think there's something different about this. I think there are actually ions. I think some of these atoms have lost electrons and became hydrogen ions. And that's a guy named Arrhenius. And so the Arrhenius definition is that when you put something in a water, if you dissolve in water, and it produces an excess of hydrogen ions, it's an acid. Yes, one more.
So if all acids chemically react with things mainly off of their hydrogen ions, why are certain acids so much stronger than others?
When we say strong, though, it means that when I put it in there, if 100% of the HCl's break up, and they do, then we call it a strong acid because of that. A weak acid, only 1 out of 100 maybe would break up into ions, so there aren't as many ions present. Now, on the other hand, I could have a very dilute HCl solution. It's a strong acid, but because there's still not too many hydrogen ions in there, I still might not get too many chemical reactions with it.
By strong, I mean like they have very potent chemical reactions.
No, I read in my definition, but the definition of strong acid is if essentially 100% of that compound breaks up into ions, then it's a strong acid. Even if you're a strong electrolyte, 100% of NaCl, put NaCl in water, 100% of those ions will dissociate. That's also a strong electrolyte. It's not even an acid.
Okay, but why does hydrofluoric acid react so much?
Okay, so that's getting a little deeper, but whatever bond holds, and we're going to get into that, the bond that holds H and Cl together, what is the ability of water to tear that apart? It must be pretty easy. It must be pretty easy to dissociate those ions. Whereas acetic acid, for whatever reason, water has more trouble ripping that H off of there, off of the acetate ion. Those are great questions. Those are great questions. All right. Well, let me show you one more thing, then I'm gonna move on. So, I may or may not have shown this to you in the 10th grade, but see this right here? Acetic acid, aqueous, arrow. I thought it was just arrow. I thought a chemical, remember a balancing equation? This plus this, arrow yields, remember that? What's a double arrow mean? What's that mean?
It goes and then returns to its.
Say it again.
It turns into one thing and then it turns into.
It's reversible. Now, reversible reactions, we have some reactions that are very reversible. They go this way, and they go this way at the same time. And yet, there are some, if I had to draw the arrows, I would have done like this. I would have drawn a big old arrow going that way to the left, and a little tiny arrow going to the right. The tendency of the reaction to go to the right, very small. The tendency to go back to the product, to the reactants, very strong. I would have drawn arrows like that. You know, every night you plug your phone in. Do you ever think about that? Well, I better plug my phone in. I can't talk to anybody. That's why I plug it in. Well, what's the science of that? Well, I got to charge my battery. What's that mean? What was happening during the day when it wasn't plugged in? You were having a reaction going this way to produce electricity. Why didn't you plug in and guess what you're doing to that battery? You see? So there are a lot of reversible reactions. Okay, well, I think that's enough of that. I'm going to move on to something really different. And I got to find the page numbers. Okay, now, here's what I'd like you to do. I don't want to be boring or anything like that, but what I'd like you to do is I'd like you to sit with somebody. And if you want to sit with more than one person, you can. But here I am on page 330. Page 330 and 331. I'd like you to read page 330, 31, and I'd like you to spend about maybe 10 minutes at the most. Spend 10 minutes and read it and talk about it and see if you could explain that graph right there, okay? Okay, let's go ahead and you can sit at the big black tables you want. Okay? And go find somebody you can sit with.
So, we should be. You're saying that the error should be larger. The error should be the same.
What equilibrium says, some reactions occur almost at the same rate this way, this way. Not the fusion, but an actual chemical reaction. Fusion is not a chemical reaction, it's a movement of chemicals. Now, so there are some reactions, some are strictly movable, right? It's almost zero goes left. Like HCl and water. It's like 100% of them are going to bring an ion. What percent is going to come back and do like the HCl? Acetic acid, it's 1 out of 100. It's an ion. Tendency to go back, even if you make it ion, it's going to be very great to come back to the acetic acid.
charges that we should have on here.
There are several ways in which atoms can interact with one another to form Gray gates. Consider specific examples of those various types of bonds. Parts of the bond.
It's identical to Big gravity. The amount of attraction between the Earth and the Sun has to do with the mass of both and the radius, the distance between the centers, right? This has to do with the charge of each divided by the radius between the centers also. And what that really means is, if you're really close, you have a great amount of attraction. If you move further away, you drop it off very quickly.
For example,
Well, we have that same thing in thermodynamics. If you have negative energy, it means that you're giving off a and it's tells you whether you're being attracted.
It's like,
The bigger the charges, the more the attraction.
That's how far you away, how much energy you are giving.
Yes, yes, and, no.
prayer
And so
involves
because-
vast
because-
devotion and profession of faith.
Yeah, yeah. The increase in.
So really, it's the same, no matter how close you
And what
are.
are the non-believers?
You want to remove it, you don't do it. There's lots of- that's an important one. I don't, I believe it's. Yeah, no, I can't. Well, I'm just saying. Getting off energy, which is really.
Because it's going to lower energy.
That's why when I start with thermodynamics,
There's one of them, it's like proton, and electron. And what's their proton, electron?
Coulomb's law also sees calculated the pulse of energy with zero protons are brought together. In this case, the calculated target energy was electrons. We've seen that a bond of electrons is two different types of forces. Reactive form optically charged ions. This bonding force of between certain chemical atoms.
More attraction and repulsion.
So that
How do you know about this graph right here? It says. That things have a tendency to go to the most stable frequencies that can be, least energy. Iron. So when these, they're really close to iron. When they're, really far away from each other, there's almost no energy. No attraction or repulsion. They don't have. How can you tell when they're what? They always have. Just find out what, to what extent are they being attracted, to what extent, that's what this is showing here. So let's make the distance between the iron ions get a little bit bigger, more stable, more stable, more stable. See this? Let's make it a little bit, turn out a little more. That's actually the case, why things get left to eat. It's just so, now, if you want this to hold back, right, so that's not as stable.
So why don't we see more diatomic coulombs?
Oh, yeah, now, this one has one proton, one electron. That's a great question. Right now, I don't know if I've ever really, I don't know if astatine really does it all, they need. So ione's pretty big, and yet it does form, diatomic elements. That's a great question. Why don't we find more diatomic elements? Now, we have things called like sulfur 8, phosphorus 4.
I've seen those.
So those now become another stable thing.
So but that's not diatomic, it's more allotropes.
Allotropes that graph again, the graph has, positive energy and it has negative energy. What does that mean? Look on the y-axis. Positive energy meant that attraction or repulsion? That was repulsion, and if we get to the negative zone, that was attraction, wasn't it? So we have this situation where any two elements, if they want to form a bond to each other, there's a spot where you have the most stable situation, like that. It's a combination of attraction and repulsion, but the most stable is that usually at the bottom of that little trough there, and that's how they know these different bond lengths, like that. Now I'm going to have you jump over. We already talked about electronegativity a little bit. You want to read that if you can, but we're going to go all the way over to 335. 335. 335. 335. I'm leaving your table, so you're going to do something else. Now, we showed you this before, that you now know that things aren't necessarily clearly covalent or clearly ionic, are they? The only one I would know is, if it was a diatomic element, what is the electronegativity difference between hydrogen and hydrogen? Chlorine, chlorine. It's 0. On that chart, it says you're clearly covalent. Some books, and I'm not sure where they got that number, but some books will go all the way up to around 0.4. Somewhere around 0.4, 0.5, they'll say if you're between 0 and about 0.5 difference, you're going to be pretty much covalent. Okay, now, what if you jump past that 0.5 mark and you go to around, and some books say 1.7, some say 2. I don't know about that. I'll say 1 point, I don't know. I think 2 is way up there. Anyway, if you get above 0.5 and below 0.2, you're not covalent. You do have some tendencies to be plus and minus, and they call that polar covalent. But if the difference gets above 2, for sure, then you are clearly ionic. Your attraction is so great, you actually stole the electron and it's over there with you. So what I'd like to show you is, at the bottom of the page 335, take a look at that picture. Everybody see that? All right. They actually have a way of, did you ever see a picture, the first time pictures came out of like planets, like Jupiter? I remember on, they used to have these things called magazines. The magazines, they have Time magazine, everybody knew about Time magazine. And they said, and the Voyager was going by there and they said, look, these are great pictures of Jupiter. And I remember seeing it, I like space anyway, but I remember seeing the picture, and here was like a blue band, and a red band, and an orange band, and another color band. I said, wow, that's what Jupiter looks like? And I think a lot of people thought that, but that's not what Jupiter looked like. And they had one of Saturn, and it also had red, and orange, and blue, and they didn't look like that at all. I said, why would they put that on a magazine? But what they did is, humans have a little bit of trouble figuring out, here's gray, and here's a little darker gray, and here's a little bit lighter gray. They would look gray. In Saturn's case, everything looked butterscotch. I love the butterscotch color of Saturn. But you could tell there was a little bit different butterscotch than another butterscotch. So they told the computer to use false color imaging. You see this kind of butterscotch? Make it red. And because right next to it, that slightly different butterscotch, I want you to make it blue because they contrast really with each other. See that? And then when you see the planet, you'll see the banding in the atmosphere. Okay, now, look at this picture on the bottom of page 335. If you had a machine that could tell you about electron density, get it? It would probably look all gray. The image might look all gray. But what if I told the computer to use false colored imagery and say, make the more electrons there are, make that gray greenish, and make the other one bluish. Now turn the page and see what happens here. Whoa, look at that. Okay. And so now you see these pictures and it says, where the electrons are spending most of their time, make it this color. Where they spend the deficiency of electrons, make it this color. That's kind of pretty, aren't they? All right, now go back one page. Now here's what I want you to do. All right. On page 335, what are the two elements in that compound at the bottom? Now this is where I need you to listen, okay? All right, what kind of bond would form between hydrogen and fluorine? Now this is not as easy as you think. electronegativities of hydrogen and fluorine and see what you see. What is the difference? What is the difference? How much?
It's polar because.
Wait, no. What's the number? What's the electron next? 1.9. That's up there. That's up there. I would say it's very much a polar covalent bond. So you draw an arrow, and the arrow has a plus sign on one end and an arrow head on the other. So which way does the arrowhead? Where is the arrowhead going toward? So where the electron density is the greatest, and the plus sign on the back of the arrow is kind of like who got left behind and became positive, a little bit more positive. See that? Now, because there's only one bond, and that one bond is polar, then what do you think about the molecule called HCl? Or HF? If there's only one bond, and that's polar, then the whole molecule is, that's the easy. Turn the page. Now, look over there on the next one, down to 8.5. What are the chemicals involved in the first drawing? Okay, now, what I'm gonna do is, I'm gonna, you be able to see the screen from back here? Here's what I'm gonna do, I'm gonna draw one for you, and I'll let you do the rest of it by yourself. Okay, now I know you're far away, but I want you to look up here. All right. All right, I'm going to magnify this a little bit. So I think you'll be able to see it. All right, does everybody see it?
Yeah.
Okay, so now, what I want you to do is, here's a bond between hydrogen and oxygen. What is the electronegativity difference between those two? This was 2.1. This is 3.5. So 1.4, right? So what category does that put that bond in? Okay, now, let's do over here. So you're going to draw an arrow toward the oxygen atom. See that? See that right there? That's a dipole moment. Now go over here, do the same thing over here, and just say, well, that's also going to be polar covalent. So I draw another arrow like that. And so the two arrows, though, I have to think of them as, what's the whole molecule going to be? And so what is this vector plus this vector? It's that vector there. And so we now know the entire molecule will end up being polar because it has, here's a word now, it has a net dipole moment. Get it? A net dipole moment. Now what I you do is to do the rest of the examples, and these are the same ones I'm going to use on the test. Do the same one, do all the rest of them just like I did, and do that page and the next page. And then there might be one on the other page, on the next page after that.
Okay, so the nitric acid, they're all, that's what I'm thinking. They're all pushing. Okay, so what is this? Yeah, there's more nitrogen. You're still because of it's green. If it was green, you don't know where the source is. No, but there is no point. That's just if it was ammonium.
No, the lead's like
They're
41.
It's like 41.
Red isn't necessarily negative, it's just a concentration of ions. Correct. Small, slightly. That's one, that's H2O. This would be,
Oh, yeah, yeah, so like, with the purple, with the purple.
Shaggy was definitely Shaggy was definitely Shaggy and Shrek would be the ultimate. Shaggy and Shrek would dominate the universe. I should
Really, like, you're only taking fiction out of your class. Like, history, literature, and
Really quick, sorry, so this is the space out here, this green area, what's
Different shades, all the time here, most of the time here, then here, then here, and then there's just not time.
and then is this space, like, is this an actual shape that's left to hold, or is it just like, this is what the majority
This
is?
is, we explained, this is our polar.
This is our religion.
Electrons have a configuration within an atom, but when they form bonds, they have a configuration within the molecule.
So this is the,
Now,
this is the,
electrons belong to
this
the
is the.
molecule. We share. So,
Yeah,
that's what I'm saying.
What was the one?
The effect, the effect of these electrons will have a field. It's sort of like that shape. So this is the natural field that that's from real data. Okay, got it. That's from real
Look,
data.
this is the colors. Yeah, and then it's full of.
Alright. See if you understood this, right? So, Yeah.
Think about it like a background, it's a different layer. Like yours looks like the red is the, and all the other colors are on there. That's where the.
Yeah.
I need to remind Lindsay to not leave school without me. Cause she would do that, cause she has art last month, but then I'm not.
Yeah, I got her first play the pool.
Oh my gosh, did you guys do the reading response yesterday?
Yes.
I was doing it during thesis. I had it so hard.
I did it so hard.
It's like a research paper.
And the paper itself took like 20 minutes to write, trying to understand what I was writing took me
Yeah.
forever.
Which one did you do?
I did degree words.
That's what I'm doing too. I'm so confused. I read
Concepts of multiplicity.
I started reading the matter.
Yeah, they are good.
And it was like talking about a staircase for the first like 5 pages.
Yeah, I know, it gives you way too much
I
information.
was who knew it? Staircase would be so complex.
Oh, love that.
Yeah, but like, you know, right.
More is coming, so.
Yeah, that's so. Don't the boxes on those masks say that you can't like buy them individually?
Probably.
Like it's like individually wrapped. I mean, you can't buy it. You can always buy it. No, you can't buy it. Most of them. The thing that goes like that is actually just
Hopefully there's something breakable in
I don't think you hear anything.
Gets them used to working again. And sort of.
And so I was like, if it's clogged enough.
It was just I think it's more like.
No, my space.
Worked with
I was like, my phone tells you not to serve. Why is it on? Why is like the stuff?
It's also like I mean, it's $20 per box of 50. Those aren't even paid anything, they just gave their money. We have 500 boxes. Which I can fix that. I'll mention that. Yeah. That could probably make sense. We should take large advance.
It's because I watch it. So it's not yeah, you're supposed to watch it. It is. I was scared that shit. Like I turned around to see it. No, I do have one. I called you out twice. It was during like class. Oh, good. Oh, sorry, man. It is. Oh, sorry.
Okay, here we go. Let's get going, okay?
It's like having a.
Very busy day for me today.
Put it anywhere for Troy.